All right, so on this particular problem, hopefully you recognize that this was a secant problem, secant theta when you do the substitution. So x is going to be 3 secant theta, dx is going to be 3 secant theta tangent theta, d theta. And then when you set up your reference triangle, the hypotenuse should be x, the adjacent leg should be 3, and then the opposite leg should be the square root of x squared minus 9, which is what we have here. And then what I went ahead and did is I've kind of skipped a lot of steps. And then eventually you'll get to this point here where you'll have 3 integral secant squared theta minus 1 d theta. And then, of course, when you integrate that, you get 3 tangent theta minus 3 theta. Now, you'll notice that my limits of integration up here were originally 3 and 6. But since I've done this substitution, what I've done now is I went ahead and changed. For example, I changed 3 and I changed 6 to those appropriate values based on the substitution. Anyways, you will get a final result of 3 radical 3 minus pi. This is the exact answer, or as exact as you can get it. So if you want to check that later, that'd be great. But we're going to go ahead and move on now and start looking at today's stuff. Okay. So hopefully you've already watched the video that I made on this lesson. I posted it last Friday morning at 9 a.m. And we're going to be looking at this thing called partial fraction integration. It's kind of the last trick, if you will, that we're going to use in terms of integration. We will talk about L'Hopital's after Thanksgiving. And then the very last lesson that we'll do this semester is something called improper integration, which sounds kind of interesting. And it actually is very interesting. But this is going to be kind of the last trick of the trade. And I'm actually just going to start this off with an example. Again, assuming that you've watched the video I've posted. So basically, if you try to do a U substitution here, or if you try to do a trig integrate, none of those things are going to work in this problem. So you're kind of stuck in the water. So the big idea behind this is we've got this 5x plus 5. Well, notice that this, and of course the numerator could be factored too, but the denominator here could be factored to x plus 4, x minus 1. And you can check that if you'd like, but that's all we need to do here. And what that tells us is since that denominator can be factored in such a way, well, what we can do is we can do a partial fraction decomposition. Now, the key to this is we're going to have to figure out some number A and some number B that will make this a true statement. So what I'm basically telling you, it's kind of like this. If you had 1/3 plus let's say 2/5, and you had that, if you wanted to add those together, you'd get a common denominator and you'd add them together and you'd change this into one fraction, right? We're kind of doing the same thing, but in reverse. That's the idea. So now at this point, to do the work, I'm basically just going to use algebra techniques. I'm not doing any integration yet. So what I want to do here is I'm going to multiply through by this denominator. And when I multiply this side by the denominator, I'm just going to end up with 5x plus 5. When I multiply this denominator over to this side, the x plus 4 factors will cancel, but the x minus 1 factor will not cancel, so it will be left on the top. So this is going to be a times x minus 1. When I multiply this denominator by this second term here, the x minus 1 factors are going to cancel, and then you'll be left with b times x plus 4. And so now what we're going to do is we're going to solve this equation in kind of an interesting way. First of all, I'm going to write 5x. I'll leave that in red. And then in purple, I'm going to put plus 5. Now over here, I've got a times x, which is ax, and I've got b times x. So those are my x terms. So I'm going to write those in red like so. And I'm actually kind of doing 2 steps in one. Ax plus bx could be rewritten as a plus bx. Similarly, and now I'm going to do this part in purple, I've got this 5 here. Well, a times, by the way, a is a constant. A times -1 is -a, and then b times 4 is 4b. So then over here, what I'm going to get is 4b minus a. So the key thing to note at this point here This is my linear term, and this is a linear term. This is a constant term. This is a constant term. In other words, we know, and I'm going to do my red work here, that 5x has to equal a plus bx. And of course, we can get rid of the x's on both sides, and we get a plus b has to equal 5. We can play the same game now with the purple stuff. So we know that 5 has to be equal to 4b minus a. So if I wanted to, I could move this a over here, which makes it a, and move the 5 over there, which makes it negative, which would make it negative 5. And now I can substitute this into my first equation. So now I'm solving a system of linear equations. So we get 5 equals 4b minus 5 plus b. So when I add this 5 to this side, that's going to give me, and I'm getting kind of low here, 10 equals, and then 4b plus 1b is 5b. Therefore, b has to be 2. And now that I have b, I can find a. I know that 5, or a plus b has to be equal to 5. So if I put 2 in for b, a clearly has to be 3. Now, please note that I have not done any calculus yet. The only thing I've done is I'm trying to convert this fraction into 2 separate fractions with a linear term in the denominator. So let's go ahead and go on to the next slide here. So I'm saying that the integral, and I'm going to use my notes here just to make sure I don't write this down incorrectly, 5x plus 5 over x squared plus 3x minus 4 dx can now be rewritten as, and I think we said that a here was going to be 3, so this is going to be 3, let me write that slightly different, not the highlighter, integral of 3 over, and I think we had x plus 4 as our first term there, dx, plus integral, and I think we got 2 for b over x minus 1 dx. And now this is trivial. You guys are very good at doing integrals involving things like this. So this is going to be 3 natural log of x plus 4 plus 2 natural log of x minus 1 plus c, and that's your answer. Oh, I've got something I'd like you to do real quick. I have a poll. If you wouldn't mind just taking a second and just answering my poll question right now, I'd appreciate that. And while you're doing that, if you have any questions about anything that has happened here on this slide or the last slide, this would be a great time to ask. Question. Oh, I guess not. Okay. Okay, I'm going to go ahead and go back a couple of slides now. So again, let me kind of summarize what we did here. I guess I should say what I did here. So I had this polynomial divided by a polynomial, and I recognized I could factor the denominator. So I was able to decompose this into 2 rational functions, and then based on that decomposition, I could then integrate using, in this case, the natural log. Now I'm going to go back to this this slide here, which I skipped over earlier. And by the way, if any of you are interested in having this presentation, which is different than the one I posted on YouTube, please just send me an email. I'll be glad to send you a PDF version of this. This right here, let me get rid of the eraser part here. This basically, if you get this, what this decomposition looks like here, this is all the examples I'm going to do today. I'm doing 3 examples. I just did the first one, and the first one was just where there was an a and a b, and they were distinct linear factors in the denominator. I'm also going to do an example where one of the linear factors is to a degree higher than 1. Like in this case, we have x plus 1. So notice, you would think that there would just be the x plus 1 factor squared in the denominator. Well, it turns out that there will be 2. There will be the x plus 1 by itself and then the x plus 1 quantity squared. And then the third and final example that I'm going to do is going to involve a factor that cannot be broken down into a linear factor. In fact, it's a quadratic factor. And so you'll notice that this numerator looks different than the other ones. These a, b, and c, these are all just real numbers. Over here, we've got a linear function on the top. So anyways, this is kind of the gist of this whole partial fraction decomposition. So I'm going to go ahead and move on to my second example here. And notice that it has a degree 2 in the denominator. And notice it's already factored. So again, what I'm going to do is spend, honestly, most of my time setting this up before I do the integral. So what I want to do is I want to take this 1 over x quantity x minus 1 squared, and I want to rewrite that in a way that it's going to be a over x plus b over x minus 1 plus c over x minus 1 squared. All right, so here's what we're going to do. So once we have it written like this, now notice some of you might think, well, Mr. Allen, that technically is a quadratic term. I realize that, but it's a duplicity. In other words, it's this same factored. It's just squared based on our polynomial. So I am still leaving this numerator as just a real number c. So what I'm going to do now is I'm going to multiply both sides by this denominator. We're like clearing the fractions. So when I multiply the left side by all of this stuff, I get just 1. When I multiply the right-hand side by this, now here's what we got to keep in mind. I'm multiplying by this all the way through. So what's going to cancel here is just the x's, but this x minus 1 squared will not. So this is going to be a times x minus 1 quantity squared. Plus, when I multiply this to the second term, only one factor of x minus 1 is going to cancel. So that's going to give me b times x minus 1. When I multiply this denominator to the third term, the b minus 1 quantity squares are going to be canceled. So that'll just leave you with c times x. So now I'm going to do a little bit of work here, and I'm going to try to be careful to not make any careless mistakes. There we go. And now I'm going to write, this is kind of an important part here. I'm going to write ax squared plus, and then I'll do this in green. I'm going to write 0x, and then in red I'm going to write plus 1 on this left-hand side. Hopefully you would agree with me that 1 is equivalent to this. Now what I'm going to do is I'm going to try to group everything together in blue here that has an x squared. So those have an x squared. So notice there's an a plus bx squared, right? So I'm going to write that as a plus b x squared. Next up, I'm going to try to group all of my linear terms that just have an x in them. I see an x here. I see an x there. And I feel like I might have made a mistake here. Let me make sure that I did not. Nope, I didn't. Okay, we're good. Okay, so these two terms have negatives in them, so that's kind of unfortunate. So I'm just going to write it negative 2a minus b x. And then, of course, we've got the last thing to deal with, which is just our constant term x. So we've got to deal with this guy here and this guy. Ooh, I think I just made a mistake. For sure, I made a mistake. Hold on. That should be included. That has an x in it as well, doesn't it? Okay, I have screwed that up. This term here should also have an x in there. So I hadn't made a mistake, but I just did. Oh no. I think I just went to the next slide, I hope. Yay. Okay, good. All right, we can fix that. See how this term has an x in it? It has to be included here as well. So I'll put plus c there and then an x. The only linear term there is a. Okay, so that's going to be just this one guy by itself. So that's just plus A. This guy here should have been green. So I apologize. Notice everything that's green had an X in it. So that's this term, this term, and this term. Well, it should be pretty clear here. You know, A is clearly going to be 1, right? Because it's the only constant term. So A has to be 1 in this example. Now, let's see if we can figure out what A plus B is. Well, that has to be 0. So if we look at our blue